Mostly, I would like to present some geometric inequalities on Riemannian two spheres. And there is a couple of reasons to do that. One reason is that it's surprising how many questions for Riemannian two spheres end up having quite intricate solutions. The other reason is that some geometric inequalities generalize to higher dimension, but are simply easier to present in dimension 2. And some inequalities we would like that they generalize to higher dimension, but don't know how to do it, and some maybe don't even generalize. So I will begin with the theorem of Lusternik and Riemann, and hopefully the effective version of this theorem will give some motivation to other questions. So this is theorem of Lusternik and Riemann. I think there are many ways to spell their names, and hopefully this is one of them. On every Riemannian two-sphere, there exist at least 3 simple periodic, of course not trivial, geodesics of index at least 1. And so now that we know that those geodesics exist, it makes sense to ask about the upper bounds. So the question is, can one bound their lengths from above? By some other parameters. So by other parameters, I mean maybe by diameter. Well, one can ask about area, but that's not going to be possible. Or maybe both diameter and area. Okay, so that's a reasonable enough question. And right away, let me tell the answer. So this is a theorem that is joined with Evgeny Liakumovich and Alex Novutovsky. That in some ways one can view as an effective version of the theorem of Lusternik and Riemann, that on every Riemannian two-sphere there exist at least 3 simple periodic geodesics of lengths at most 20 times the diameter. So d is the diameter, and that's how we'll denote it. Okay, so let me just briefly discuss well, the history. It's a short history.
The long history.
The long history? No, no long history. So
It is a long history, though.
okay, well, I'm gonna give you the brief version of this long history. So I'm going to just simply begin with a result of Krog. So of course, you know, if you want to bound 3, well, one should begin with 1, and Krog gave the first upper bounds for the shortest periodic geodesic. So he did not care about how good his bounds were, and he did not care about whether the geodesic is simple or not. He just gave the first upper bounds, and they were in terms of, it was 9 times d, and it was 31 square root of area. Right. So let me say right away that we cannot bound the length of the second. I put the second in quotation marks because there may be more than one. We cannot bound the second longest periodic geodesic on a sphere in terms of the square root of area, because one can look at an ellipsoid of revolutions that is long, and so the length of the shortest periodic geodesic is going to be long as well. Second, yes. So one cannot, if we just want to use areas, that's not going to be possible. Okay, so let me just briefly discuss the proof of this theorem. Well, in order to discuss the proof of this theorem, I really have to begin with the proof of Lusternik and Schnirelmann. So how does one prove the existence of those geodesics? One has to consider the space the space pi of m, and it has the space of non-parameterized curves on n. M is a Riemannian two-sphere. Now here, this is M sitting inside this pi of M. And well, one can also denote it as pi 0 M. One can identify it. This is just the space of constant curves. We now consider the homology, the relative homology, with coefficients in Z2. Okay, so in fact we consider it in dimension 1, 2, and 3. Now there will be some non-trivial cycles here. And those non-trivial describes and the representative of cycles in a second. And those non-trivial cycles will give us distinct simple periodic geodesics. So there are a couple of things. So why are they simple curves? Yes, sorry. Simple closed, of course. Sorry. So right. So there are a couple of things here, right? I mean, we want that we define a flow, right? I mean, we would like to define a flow that does not, we have simple curves here, we'd like a flow that does not create self-intersections. So because it does not create self-intersections, we know that the critical point is going to be when we decrease the length, that the critical point of the length function is going to be a simple periodic geodesic. Now, maybe perchance all of those, so we're going to have representatives, I'm going to call it maybe W1, W2, and W3. Maybe they all are going to get stuck on the same geodesic, but in that case, Listernik and Schnurman have shown that we have the whole critical level, so it's going to be infinitely many. But it's not possible for them to get stuck on the same geodesic iterated many times, and that's because that's not going to be a simple curve anymore. Okay, so how do I describe the representatives of H1, H2, and H3? Let me first go to the round sphere and describe it on the round sphere. And I'm going to call them Z1, Z2, and Z3. So Z1. So this is a round sphere. And I'm going to take all the planes that are parallel to the XZ plane. I'm going to move them and cut the sphere. It's going to create a slicing of a sphere. So I'm going to have those curves here. I'm starting from the south pole, and via the parallels of the sphere, I'm moving up to the north pole. This is a relative cycle, okay? So that's the first representative. Does it make sense? Okay, so here is the second one. So I have here a round sphere. Let me start from the first cycle. So remember, I'm taking this plane, I'm moving it upwards, and I'm looking at the slicing. Now the two cycles are gonna be represented by a two-parametric family of curves, right? So I'm going to now take this plane, I'm going to continuously rotate it until I reach the angle of pi. And as I rotate it, I move it and slice it. So I'm going to create a bunch of curves like this. Okay? Until I go back, well, I go back not to exactly the same cycle, but if I put a minus sign to it, it's going to be the same cycle. So that's why I have coefficient Z2. And finally, Z3. I don't have to draw actually anything. I just take all circles on S2. Okay, so what are W1, W2, and W3 are? Well, since I have a Riemannian two-sphere, I have a diffeomorphism from a round sphere to M. And so W1, W2, W3 are induced by F star. Okay, so I don't know how this sphere looks. It can look kind of nasty. So if I look at the images of, well, Z1, Z2, Z3 under F, what I'm going to have? Well, I'm going to have something bizarre. I don't know, maybe a curve, one of the curves will look like this, right? So I'm going to have some long curves, fairly long curves there. At least from the beginning, we don't know how to control the length of those curves. If we could control the length of those curves, that will give us the upper bounds for the length of periodic geodesics. So the question then becomes, is the following. So can we really come up with a map from S2 to M so that the lengths of those curves are controlled in terms of, well, right now we're worried about the diameter. Can we really, so to put it in other words, right, I mean, can we sweep out M by short in terms of diameter curves? Well, actually, we don't. We need even more than sweep out. We actually need some. We need a slicing. We want that those curves are. So in fact, we need a slicing. So can we really? Well, I mean, so and that brings us to the second question: is there a difference between a sweep out and a slicing? So suppose, I mean, we are looking at an optimal sweep out. Should it be really a slicing, or must the curves have self-intersections, or should they intersect each other? Okay, so, well, the answer to the first question is kind of simple. Can we sweep out? Always sweep out. The answer is no. We cannot hope to always sweep out by curves that are going to be short in terms of diameter. And the answer to this question was obtained by Evgeny Lyavkumovich. But that is based on an earlier result, so that he produced a family of metrics where the sweep outs are necessarily long. But this is based on an earlier work of Frankel and Katz. So the work of Frankel and Katz came as an answer to the following question of Gromov. Okay, so Gromov asked, let us consider a Riemannian 2-disk of diameter d, and the one that has the length of the boundary is L. Is there a function, or is there a constant such that there exists a homotopy of the boundary of this disk to a point over curves of length bounded by some constant times L plus D. Okay, so they first have constructed a counterexample to, well, I mean, so the negative answer to this question, and then Evgeny, based on that example, constructed his example. Okay, so since we cannot really sweep out a sphere by short curves, then what are we going to do? Well, the first step is the following. The first step will be, okay, I'm not quite happy with those representatives. So let's find representatives that are homologous. Okay. So I'm going to find, now I'm going to describe Z1 tilde, Z2 tilde, and Z3 tilde. And I will be happy at working with those. Okay, so I'm still in a round sphere for now. Actually, I'm not going to put axis. I just would like to quickly redraw the first representative in a little bit different way. And so I start, let's imagine that this is my south pole. I start here. I go till the equator, and then at the back, I return to a point. So I would like to consider something a little bit different. Okay, let me look at the round sphere. Let me fix a meridian that I'm going to call M0. And typically, my curves in the meridian are going to look like this. So this is going to be a meridian M alpha. It makes an angle alpha. And this is going to be a meridian M minus alpha. It's going to be still angle alpha, but on the other side. And my typical curves are going to look like those two curves concatenated. So I'm going to go along the M sub alpha and then return along M sub minus alpha. Okay, so you should kind of imagine, well, there are two meridians at M0, and I'm going to open them, and then I'm going to close them at the back. Okay, so that's not quite what I would like to do, because I cannot really take, right, I'm interested in simple curves. I cannot really take curves that goes back and forth here. So fine, so in the neighborhood of this meridian, I'm going to just slowly split apart. Okay? So that's Z1. I think, you know, I mean, it's kind of not so hard to see that those are going to be homologous cycles. I mean, you can look at it this way. You can take those circles, sort of stretch them out simultaneously. Okay, so here is Z2. Okay. Yes? Okay. So I remember that I obtained Z2 from Z1 by taking this picture and rotating it by pi. So I had something like this. And then I rotated it and obtained more circles, right? So I'm going to do the same to this picture right here. I'm going to rotate the meridian M0, okay, by pi. And so as I'm rotating meridian M0 by pi, so I had those curves that look like this. And I also am going to obtain curves that look like this, right, as I'm rotating. Yes? So in essence, what I'm doing is I'm taking all the pairs of meridians. Okay, and so this 3 is going to be a little bit more difficult to visualize. So remember that these three are all the circles. Okay, so instead of taking all the circles, I'm going to take pairs of meridians that have the same bisector. Maybe something like this. And something like, oops, I should use different color. And something like this. And I'm going to follow one by the other. Okay, so I'm going to go along one. And I'm going to go along the second pair. Okay? Well, not quite. I mean, I want the self-intersection, but those are sort of technicalities. So why so? Why can I mean, I'm going to wave my hands a little bit. So why is it the same as taking all circles? Well, if I draw a circle here, I can, let me choose a line. And let me choose two circles that are tangent to the line that traps this circle right here. Then you can imagine taking this circle and stretching it out until it looks something like this. Right, so remember the last time we have for Z1 we have the family of all circles. So now instead of those circles I have something like this. Am I drawing this curve? Yeah, okay. So instead of this circle I have this curve that's stretched out like this. And I'm going to take those two curves and I'm going to stretch them until they're going to look like pairs of meridians. Does it make sense? So, so this is now the third representative. It's going to be these three, well, tildes here. So this is the 2 tilde, and this is going to be these 3 tilde. Okay, and so notice now that if I have something, so now I'm, of course, right, I mean, I'm interested, this is a standard 3 sphere, but what I'm interested is M. So let me look at my map F from S2 to M, diffeomorphism, right, again. And let me look at W1 tilde, W2 tilde, W3 tilde induced by F from Z1 tilde, Z2 tilde, Z3 tilde. And so notice the following. Let me go back to Z1. I remember that Z1 is produced really, you know, I take some meridians, right? Well, all of them are produced in the following way. I take all those meridians, and some ways I can concatenate those meridians, right? So suppose I know the length of the images of those meridians. If I know the length of the images of those meridians, that will give me an upper bound for all those periodic geodesics. Does that make sense? So this is something that we call meridional sweep out. I hope I spelled it correctly. I think meridians are spelled with I here, but meridional is spelled like this, I hope. Okay, so, right, I mean, this is what I hope to get. Right, I mean, is that I really know, I mean, I look at the image of each of those curves and really can say what the length is. And of course, again, this is kind of hopeless in general because of the theorem of Evgeny. So this is how I'm going to proceed now. Okay, so, well, okay, so consider M. And let me take 2 points P and Q that are maximal distance apart. So they're diameter apart. Okay, then by Berger lemma, Q is a critical point of distance function with respect to Q. And so here's an observation of Kroc. We can split the sphere, we can split M into the digons that look like this. So an angle of each of the digon is going to be less than pi. Okay, so now if we apply the curve shortening, let's say, we are using the Birkhoff curve shortening maybe not quite good. Okay, so we need a little bit careful. We need actually the curve shortening processes that do not create self-intersections. Well, in this case, the Birkhoff curve shortening process is going to work just fine. Okay, it's not going to create self-intersections. So, so we split it. So we apply the curve shortening, and because the domain that we have is convex, the curve is going to stay inside. So there are a couple of possibilities. So here is possibility 1. A nice possibility, really. There are 2 cases. So let me write like this. Apply suitable curve shortening. And there are 2 possibilities. So case 1, we will contract to a point. The curve contracts to a point. And it contracts to a point in every such digon on M. In this case, it is still an observation. Okay, this is maybe not an optimal way. I'm not doing it. I'm not trying to get the constants be as good as possible. It's not an optimal way. But still, by observation of Kroc, but really it's not a very hard observation, the curve can be effectively constructed as a loop. So simply, let's take some point. Let's connect this by a minimal geodesic. And I'm going to now construct it having this point fixed over short curves by going like this. I'm going to follow this minimal geodesic to a curve, go around the curve of the trajectory, and return back. And if I shift it a little bit, I can do so that the curve does not trace along portions of itself. Does it make sense? So if I can contract it like this, I can contract it as a loop. But also, here is a simple observation that we used many times in our papers, that and really is just topological statement, just adding some distances to it, that if we can do it, we can now create a path homotopy between, let me call this E1 and E2. So here is, so maybe this is observation 1, and this is 2. There is a good, by good I mean over short curves, path homotopy. between E1 and E2. Okay. Let me just quickly demonstrate how it's done. So there's good path homotopy. What is it, right? I mean, so we know, so we have E1, and we have E2. And now we know that there is a homotopy. If I concatenate, if I follow E1 by E2, then there is a homotopy of this with a fixed point. Well, I can do something like this. I can start with E1. And I can start growing a short loop out of this followed by E1. OK, so now my curve looks something like this. I will be a little bit careful so that my curve doesn't have self-intersections. OK, so it's going to look something like this, yes? And well, this length is controlled. This is, of course, bounded by D. Is exactly D, in fact. OK, then at some point, I'm going to have something like this. Right? And then I just can cancel this. And so I'm going to be left with this. OK, so if in all of the domains I start contracting this curve and it does not get stuck on a periodic geodesic, then I have a vertical sweep out, and the existence of those three short simple periodic geodesics will follow from the existence of this vertical sweep out. So a more interesting case is what happens if we get stuck on this periodic geodesic. So this is case 2. So I have those digons, and I contract it, and I do get stuck on a periodic geodesic. But it's one periodic geodesic, and I want to have 3. OK? So in this case, what I do is let me pick a point here that is the maximal distance apart from the boundary. And as Berger lemma generalizes to a situation like this, I can then break, by the same token, this domain into a number of convex domains and repeat the process. You know, I can contract, either I contract to a point, which is good, then I'll create the vertical sweep out of this guy, and which it will extend to vertical sweep out of the whole thing. Or I maybe get another geodesic, and if I get just one more geodesic, I will repeat the process. But if I just get a couple of geodesics, then I'll stop. OK, so I just need 3. OK, so there can be a little bit of problem. I said that we want an effective version of Lusternik and Schnirelmann theorem, but maybe it's not quite an effective version of Lusternik-Schnirelmann theorem, because Lusternik-Schnirelmann theorem states that those geodesics that we are going to get are going to have index greater than or equal to 1. Here, we actually are getting some geodesics, but those geodesics can have index 0, the way we are getting them. The only way we can assure that those geodesics have index at least 1 is we do get them from a sweep out, and sweep out we cannot have in terms of the diameter only. So, however, and remember that I mentioned mentioned the question of Gromov, and then the answer by Sidney Frank and Misha Katz. They also asked, well, OK, so you cannot sweep out, you cannot really, OK, so you have, let's say you have a disk of diameter d, area A, and the length of the boundary is L. Can you contract the boundary this is a question due to Frank and Katz. Can you construct the boundary over the curves whose length is bounded by some function of A, L, and D? And together with Evgeny and Alex, we have shown that the answer to this question is positive. Yes, you can do it. And in fact, you can sweep out a sphere by curves if you want to bound the length of curves in terms of both the area and the diameter. So if you allow both area and the diameter, then you can do it. And in fact, we have gotten the following result then. So this is again with Evgeny and Alex. So let M be a Riemannian two-sphere. Of area A, diameter D. There exist at least 3 simple periodic geodesics of index of length that is bounded by okay. So this really is an effective version of Lusternik and Schnirelmann. Well, I have 15 minutes, and I have one more question to discuss. So I have mentioned in passing the following.
There is a package from a logarithm of square root of A divided by
Yes.
logarithm of square root of A divided by D.
What does it say here?
Logarithm of the ratio square root of A.
Yes. Okay. Oh, you're worried about the line being too long. Sorry. Okay. Okay, so the questions that I have mentioned in passing is, so how different are sweep outs as if the best sweep outs and slicings really are? And actually, just because I don't have that much time and to make it simpler, let me talk about the disk. So let's say we have a Riemannian two disk. And suppose I am contracting the boundary of this Riemannian two disk to a point. Now, and I'm trying to contract it over in the best possible way to make the lengths of curves as short as possible. So it would be nice if the homotopy looks like this. Right? And that's usually what we imagine. However, because of the topography of the disk, I mean, we don't know. Maybe the disk has some hills or some valleys. And maybe as we contract the boundary of the disk, what happens is something like this. So we start, maybe the curve will develop some self-intersection when we want to go around the hill. Or maybe it's more effective to start intersecting other curves and to go like this. So the question is it really necessary? I mean, is this question clear? I mean, so do we really, when we're trying to contract the curve in an optimal way, do we really have to produce these pathological things like this, self-intersections, intersections with other curves? And remember, when we were trying to prove this effective version of Lysternik and Schnirelmann, we really wanted to have slicings, right? So we really wanted to have no intersections. And that's the only situation where we really don't want to have any intersections. So, well, so interestingly enough, this question was solved in stages. So let me first mention the result of Greg Chambers and Evgeny Lyakumovich. So this is theorem. So actually, they did it in more generality, but I'll state it like this. So let D be a Riemannian 2 disk. Then, if there is a homotopy of the boundary of this disk to a point via curves of lengths bounded by L, well, let me just write less than L for convenience, then there is an isotopy. To some point over curves of lengths bounded by L. Moreover, they have proven the following. So given a sweep out of a Riemannian 2 sphere which is composed of curves less than L, of lengths less than L, there is a slicing of Riemannian 2 sphere. There is a slicing by curves of lengths less than L. This in particular solved a long-standing conjecture of Michael Friedman. So the idea being that if one can prove a similar result in dimension higher, in dimension 3, then that would give a geometric proof of point-correct conjecture. Okay, so that's stage 1. So right now, right, I mean, Evgeny and Greg Well, I mean, they have shown that creating self-intersections would not be an effective way of contracting the boundary of the disk. So really, you have to contract it, or if you want to contract it, you have to, but you can as well contract it over curves, over simple curves. But they did not do anything about curves intersecting each other. So that's actually was stage 2. And this is a paper with many co-authors, some of them computational topologists. So this is with airing chambers, Greg chambers, Arnaud de Mesme, and Tim Opfelders. So let D be a Riemannian 2 disk. Suppose there is a contraction of the boundary to a point through curves of length less than L. Then there is a monotone homotopy contraction to a point over curves of length less than L. So this is so by monotone homotopy, I mean a homotopy that does not have in which the curves neither have intersections nor intersect each other. So really, the picture looks the way we would like to imagine it. Something like this. And apparently, it was a well-known question in computational topology. So I have exactly 5 minutes to discuss the proof. Let me try to discuss the proof a little bit and to point out that it's really not that simple. So we have a disk, and the first step, of course, would be to get rid. I mean, so we have some homotopy, and the first step would be to get rid of self-intersections, and that we can do using the theorem of Greg and Evgeny. Okay, so now suppose we have a homotopy that looks like this. How can we possibly get rid of curves intersecting each other? There are a couple of ideas. Well, okay, so first let me discretize a homotopy. In fact, you know, the way I have drawn it, I mean, that's the only way I can draw it, right? I mean, so let me discretize a homotopy. So I have a sequence of curves. They start from the boundary, and they end with a point. And let me look at gamma sub I and gamma sub j in this discretized homotopy. This may be gamma sub I, and this is gamma sub j. And suppose the index j is greater than I. Then this is not the picture that we want. right? I mean, we want that this gamma sub j lies in the disk bounded by gamma sub I. That's what we would like. So the first natural idea is let's exchange those pieces a little bit, okay? So, well, this is the place where, on this interval, whatever it is, right? I mean, we are happy with what's happening because this part lies where we want it to be, but this is not something we're happy with about. So the idea here, well, maybe we can switch those pieces, maybe not even switch. Let's see which one is shorter. So whichever one is shorter, then we're going to make, so let's say maybe this one is shorter, then everything is going to become like this. Then gamma sub I will just follow this curve, and we're going to be happy. But, and this is again the place, so this again is the place where about which we're happy. This one we're not happy, so let's again, choose the shorter one. Maybe this is the shorter one this time, so maybe let's switch it like this. Okay, so this is a very naive idea. If it worked, it would have been fine, but it does not, right? I mean, because the intersections don't have to be simple like this. I mean, intersections, in fact, can look something like this. So maybe this is gamma sub I, and maybe gamma sub j intersects it like this. And of course, we are not performing this switching to just two pairs of curves, right? We would like to perform this switching to the whole family. So the worst situation is when we have something like this. So this is now, so we have some curves, and they're behaving monotonously, nicely like this. And then maybe at some point we have gamma sub j, and gamma sub j looks like this. I'll draw a couple of more curves. And what really worrisome is this curve, the interaction between this white curve, maybe I'll make it not white, I'll make it green. Okay, so what's really worrisome is the interaction between this green curve and this blue curve right here. They are tangent right at this point, but in fact, if we want to switch the pieces of this green curve with pieces of blue curve, there is not a unique way of doing that. And this the lack of uniqueness creates a discontinuity in this whole process. Okay, so in order to solve this, so this is, well, the first main difficulty, because as we are trying to resolve this main difficulty, there is a bunch of more that's going to come up. Okay, so in order to resolve this difficulty, we introduce something that's called merging lemma. So that probably is the second idea. Merging lemma is something that allows to glue two monotone homotopies. But to organize the proof, we also introduce something that's the idea of zigzag. So let's now say we have a homotopy like this. We can show, in fact, that there exists a homotopy of short curves that's going to be organized in the following way. So you start contracting a curve. You move forward in a monotone way. Then you stop, and you move backwards. Maybe obtaining curves like this, also in a monotone way. Then you stop again, and you move forward again. Maybe obtaining curves like this now, etc. So you move. So you can introduce a homotopy. You move forward, backward, forward, backwards. It's called the zigzag. Now, what is the best possible zigzag? One can show that the best possible zigzag is, in fact, just going to be a monotone homotopy. So I'm going to stop here.